4.1, right triangle trigonometry. So first we're going to look at the right triangle definitions of trig functions. So the mnemonic device we normally use for this is SOHCAH. And hopefully remember this from Algebra 2 and Geometry. And so that means if I have an angle here, we talk about there being the adjacent, the opposite, and the hypotenuse side. So my hypotenuse is my longest side. That's always across from my right angle. So this is going to be my hypotenuse. You know, let's just label that an H for hypotenuse. And I will leave this my theta. So if this is theta, then my hypotenuse is always opposite the right angle. And then my opposite side is going to be opposite of the angle I'm looking at. So we have two legs, like this is a leg right here. And this is a leg over here. So we have the opposite leg and we have the adjacent leg. So the adjacent leg is going to be next to our angle. Our opposite leg is going to be opposite from the angle. But the hypotenuse is always the longest side, and the hypotenuse is always across from the right angle. So that's how you can tell the sides. So you can tell if we were going to put theta up at this corner instead, my hypotenuse would remain the same, but the opposite and adjacent legs would switch. And that's going to create a lot of the patterns that we see for trig functions. So SOHCAH means sine is my opposite over my hypotenuse sides. So sine of theta equals O over H. Cosine of theta is my adjacent over hypotenuse sides, so A over H. My tangent of theta is my opposite over my adjacent. So we're always doing these trig functions of an angle. I can't just write tan equals O over A. I have to say tangent of theta because it's the tangent of an angle. My cosecant is going to be the reciprocal of my sine. So this is HO. Secant is reciprocal of cosine, so HA. I'm writing a little bit neater now. Cotangent is A over O, sorry, because it's reciprocal of tangent, which means I could also write my cosecant as 1 over the sine of theta. My secant I could write as 1 over the cosine of theta. And my cotangent I could label as 1 over the tangent of theta. So cotangent and tangent are really obvious from the names that they are reciprocals. Cosecant and secant are not so much. So I always remember that the cosecant starts with a C, but it's reciprocal of sine that starts with an S. And then over here we have secant of theta is the reciprocal of cosine because we have C and the S together again. So they're kind of opposite. Another thing I wanted to mention here on this page is our Pythagorean triples are a really good thing to remember. It will save you a lot of time. So we're just going to list those here. So triples would be like 3, 4, 5. And again, my hypotenuse is always my longest side. So the 5 would be the hypotenuse. 5, 12, 13. 8, 15, 17. And 7, 24, 25. So there are other triples, but these are the ones with the smallest numbers, the ones that we use most often. So for the first example, we're going to evaluate all 6 trig functions of the angle. That means we're going to find the sine of theta, the cosine of theta, the tangent of theta, and then when we find sine, we'll find cosecant of theta, secant, and cotangent. And I like to line them up. So I'm doing sine, cosine, tangent first, and then I'm doing the reciprocal functions right next to it. So the first thing I notice is in order to do the 6 trig functions, I have to have all 3 sides on my triangle. So I could either use Pythagorean theorem. So Pythagorean theorem, I know that a squared plus b squared equals c squared, where c is my hypotenuse. And we're going to use just a simplified form of this instead of having to take the instead of doing all this and then having to take the square root and solve for c, we're just going to say that c equals the square root of a squared plus b squared. So that would be one way. I could figure out the square root of 5 squared plus 12 squared. Or I could remember on that other page the triple. And so I know that my third side, my hypotenuse, is going to be 13. So if here's my angle, my hypotenuse is 13, my opposite leg is 5, and my adjacent leg is 12. So I'm going to just label those really fast, which I don't have to do, but sometimes it's nice. We're trying to review all this information. And this is stuff that you did fourth quarter last year when we were in virtual and you were using the Florida virtual school stuff. So it might be that you don't have a good solid foundation. And so this really might be learning stuff from scratch instead of reviewing it. So when I'm doing my sine, SOHCAH again is going to be opposite over my hypotenuse. So 5/13. My cosine of theta will be 12/13. My tangent is going to be my opposite over adjacent, so 5/12. And then once I find those first three, I have to just do reciprocals now. So I'm just going to take each fraction and flip it. Unfortunately, if I have one wrong, I'm probably going to get its reciprocal wrong as well. So we really want to make sure that we get them right, and that doesn't happen. So for our second example, we're doing the same thing, but this time they're not giving me a diagram. They're giving me one trig function. I'm asked to find the 5 remaining trig functions. So I'm still finding trig functions, but I've given different starting information. So I'm going to go ahead and draw a triangle. And if they give me the sine, they're giving me my opposite and my hypotenuse sides. So I'm going to go ahead and label this angle theta. And I can label any angle theta I want. It's still going to work. And so my hypotenuse is always across from my right angle. So opposite leg would be over here. That's going to be 1. And my hypotenuse is going to be 3. And now I need to figure out the third side. So let's think about that Pythagorean theorem. If I have a squared plus b squared equals c squared, and I am solving for a leg, that means I am solving for, let's pretend a. So that would mean a squared would equal the square root of c squared minus b squared. Or sorry, a would equal, let's fix that. A would equal c squared minus b squared. And then I know when I take a square root, I'm supposed to get absolute value. I'm supposed to get a plus or minus value. But we know here that we're not going to have a positive or a negative side on a triangle. So we're just going to use the shortened form on this, where we just say that a is the square root of c squared minus b squared. And I don't have to show any of this. This is just, we're showing it one time. We're going to make sure you know where it comes from. So over here, when I find my third side, I'm going to take the square root of 3 squared minus 1 squared, and that's how I'm going to do that, which is the square root of 9 minus 1, which is the square root of 8, which is 2 square roots of 2. So now that I have all three sides, I'm going to go ahead and find my trig functions. And even though I already know sine, I usually just write it anyway, just because I'm organizing all the trig functions. And that way I have my sine and my cosecant right next to each other. Remember, the s and the c go together. They're reciprocals. So trig functions are really just a ratio of sides of a triangle. That's how we're describing this. And they only work for right triangles. We don't talk about having a sine or a cosine or a tangent if we don't have a right triangle. So my sine theta I already know is 1/3. So that means my cosecant is going to be 3. So when I take the cosine is going to be, let's see, I need to probably label this. Here's my angle, here's my opposite leg, here's my adjacent leg, and here's the hypotenuse. Remember, hypotenuse is always across from the right angle, always the longest side. So if I'm doing cosine is adjacent over hypotenuse. So 2 square roots of 2 over 3. And tangent is opposite over adjacent. So 1 over 2 square roots of 2. But we need to rationalize. So I'm going to multiply by square root of 2 on the top and bottom. So 1 times the square root of 2 is just the square root of 2. And in my denominator, I have a 2 here, and square root of 2 times the square root of 2 makes another whole 2. And so 2 times another factor of 2 would be 4. So we do need to make sure we rationalize. So when I find the cotangent, though, I won't need to rationalize because I can take 2 square roots of 2 and put it over 1. So I always kind of go back to the beginning to do that reciprocal. So just 2 square roots of 2. So last is secant, so 3 over 2 square roots of 2. And I would have to rationalize this one as well. And then it looks like we're going to get 3 square roots of 2 over 4. So a little bit of practice rationalizing on that. And again, we started with different information. We had to build that triangle ourselves. So we're just going to do a quick review of special triangles. So special triangles are the 45, 45, 90. And by that, of course, we mean 45 degree, 90 degree, and then 30, 60, 90. And these are something you're really going to have to memorize. And there's different forms of them. So we're going to write down probably 3 different forms of both. So the one I like to use the most for the 45, 45, 90, I guess I should label these, is 1, 1, square root of 2. You'll also sometimes see it where your hypotenuse is 1, and then that would mean these other sides are square root of 2 over 2. And then the third way that you could see that, I guess it's kind of like the first one. And I'm trying to draw 45-degree triangles, but they're not really turning out that way. They're not perfect. That's for sure. Is you could see it as x square roots of 2 is a really common one as well. I like the first one. The middle one you'll see like on the unit circle, but I won't do it. I'll still do the first one. I pretty much just always do the first one. I don't like having the fractions for the sides unless I'm only doing cosine and sine. So for the 30, 60, 90, this small side should be across from the small angle. So I'm going to label this one 30 degrees because this side looks the smallest. And the other one I'm going to label 60. And on this one, I like to use 1 as my short side, 2 as my hypotenuse, and then square root of 3. And again, smallest angle is across from the smallest side, and that's going to help you when you label this triangle. So another way I could label it, so let's do 60, 30 again, is sometimes you will see the hypotenuse as a 1 instead. And then this side would be a 1/2, and the other side would be a square root of 3 over 2. Again, you primarily see this on the unit circle. It's not my favorite way because of the fractions, but if you're only finding cosine and sine, it's pretty handy. And then the third way, these triangles just get worse the more I draw, is that you could have x square roots of 3, and then 2x. So you could see that as well. So really what you're getting the idea of is that I could put any number here for x, right? And I could still have that ratio between the sides, and it could still be a 30, 60, 90 triangle. So on this one, I know now you're thinking like, where's that 45, 45, 90 or 30, 60, 90, but we don't have that. We have a 35-degree angle. So I've given this angle here. This is going to be my theta, and I want to find the value of x. So when they tell you that you're going to have to round and you're finding the value of x, we're going to be using those trig functions. These are going to be calculator problems. So a lot of the stuff we do will not require a calculator. These are going to require a calculator. So if this is my angle, I have my hypotenuse. I don't have my opposite leg, but I have my adjacent leg. So if I only have adjacent and my hypotenuse, then I'm going to use cosine. So I can say that my cosine of that angle, so cosine of 35 degrees, is going to be the ratio of x over 7. And then I would need to solve that for x by multiplying both sides by 7. Notice that I am keeping x on the right-hand side. I am not moving anything around here. We always want to keep variables on the same side. 7 times the cosine of 35 degrees is 5.7, and so 5.7 is approximately equal to x. So you will see problems like that today. Last is inverse sine, inverse cosine, inverse tangent. This is how we write it. So it's like sine, it looks like -1 power is what it really looks like. But we know that -1 power would be reciprocal, and this is really inverse. Reciprocal functions would be cosecant, secant, and cotangent. And we're doing inverse instead. So inverse is going to give you the angle. So you take an inverse when you have the ratio of sides, but you want to know the angle. So that's what an inverse does. So normally when we do the cosine of an angle, I'm finding that trig ratio. Now we're saying sine inverse of that trig ratio is going to equal the angle. So it's kind of undoing it. So that goes back to in math, every operation has to have an inverse. So if we're adding, we subtract. If we're multiplying, we divide. If we have a square root, we would square. So if I have a sine and I need to get rid of that, then I would take a sine inverse. So we're going to be using that in example 5. And we're getting close. We're almost done with notes, just to kind of help with your planning here. So here is my angle. I have my opposite leg and I have my hypotenuse. Remember, hypotenuse is always across from the right angle. I don't have my adjacent leg. So because I have my opposite and my hypotenuse, I'm going to use sine. And this time I don't know my angle. And it also says round to the nearest degree, which is telling me calculator. Because sometimes you're going to get a 30, 60, 90 triangle, right? We have to kind of watch for those. But this says use a calculator. So I know that the sine of my angle is going to equal 12 over 15.7. And I'm asked to find that angle. So in order to find the angle, I would do sine inverse on both sides. And if I have a sine inverse and a sine, I'm just left with the angle. And on the other side, I will have sine inverse of 12 over 15.7. So then on my calculator, I would find this button. Usually it's going to be second function wherever the sine button is. But sine inverse of 12 over 15.7 should give you about 50 degrees. So again, when I have the sine of theta equals that, it's like what I'm doing is a sine inverse on both sides. So you don't have to show this part. I'm just trying to make really clear what's going on. And when I have a sine inverse and a sine, those undo each other, right? Those are inverse operations. They undo each other. So I'm left with theta. And on the other side, I have the sine inverse. And then when I take that sine inverse, I get my angle. So if you're looking for an angle, you're going to have to do the inverse of a trig function. This is just some vocab. I like this picture a lot to show you rather than writing out words. So if this is your line of sight, this is a little stick figure down here. Well, it's a stick figure now, and I'm looking up. This is my angle of elevation. So angle of elevation is like an angle that goes up from something from your line of sight. But then here, I think this looks like an airplane, only I don't know how to draw an airplane. So that's pretty close. But from my airplane, I have this angle of depression. And that's going to be like an angle that goes, depression would be down, right? So just to kind of help you when you're drawing out word problems. So this is the end of our 4-1 notes.